So, this is chapter 7. The title of the chapter is The Residue Theorem and its Applications. Under this chapter, you will see some of the topics which are listed for the previous topics which you couldn't complete. I just wanted to sort of put in the first two items in the previous chapter, but time didn't permit me to do that. So, starting from these two topics, this classification of singularities, the residue at a pole, how to compute residues, evaluation of integrals. This is the main topic, evaluation of integrals. This is the main theme of today's lecture and tomorrow's lecture. Tomorrow we will continue with this chapter. And then we will need one small little result, fractional residue theorem. That's it. And then lots of examples. So, this is a topic that will be illustrated mainly through examples. There will be lots of problems. And even if you take up these books of Kreyszig or Churchill or Gamelin or any of these several books, you will find lots of exercises, and I urge you to look at these and work out as many as you can and show as many as you can to your students. And really you can only get a practice on this by working through lots of examples, how to choose the contour, etc. As we shall go along, we will see. All right. So, first is a classification of singularities. So, let f be from omega minus p to c, that is on a punctured domain you have a function which is analytic. Then if f is bounded in a punctured disk around p, then p is called a removable singularity. Remember, what is Riemann's theorem on removable singularities? That is, if you have an analytic function, yes, yesterday we did this, right? We did this yesterday, that if you have a function f which is defined on a punctured domain. I mean, I could take a smaller domain, right? You are given a domain omega, and it's and the function is defined on omega minus p, and it's analytic there. So, take a small disk centered at p, right? Take a small disk centered at p. Then in that disk, what is given to you, that f is bounded in a punctured disk around p. In that disk, the function is bounded. So, now forget about omega, just focus on the disk. So, now you are given a disk, and the punctured disk, the function is analytic and bounded. What do you conclude from here? You apply the Riemann's removable singularities theorem. What is Riemann's removable singularities theorem? Yes. If you have a function which is analytic in a punctured disk, punctured at p, and if the function is bounded, then limit of f of z as z tends to p exists, call it L, define f of p to be L, then this extended function is analytic. So, really what does it mean? It means that the point p is really not a singularity. The limit of f of z as z tends to p exists. It is like saying f of z equal to sin z by z when z is not equal to 0, right. Limit of sin z upon z as z tends to 0 exists. To define the value at the origin to be 1, then this becomes analytic. So, you would not call 0 as a singularity of sin z upon z. It is really a removable singularity. That is, by defining the function properly at origin, sin z by z actually becomes analytic everywhere, right. Similarly, what it says is that in this particular situation, your function is bounded in a punctured disk around p. Riemann's theorem says that the limit of f of z as z tends to p exists. So, by defining f of p to be this limit, the function is actually becoming analytic even at p. So, p is really not a singularity. So, removable singularities will not be counted as singularities. So, thus I would say that sin z by z is analytic everywhere, right. At the origin you have to define it to be 1 and nothing else, correct. So, that is the first thing. So, it's such a thing will be called a removable singularity, because it can be removed by defining the function properly at the value p. Other thing is, suppose k is the least natural number, pay attention to this, k is the least natural number such that limit of z minus p to the power k f z as z tends to p exists and is not equal to 0. then you call P, then you say that P is a pole of order K. So, the first thing is you have a removable singularity, the next is a pole of order K. Third thing is that what if such a K does not exist? What if for every K non-negative Z minus P to the power K f z does not have a limit as Z tends to P? That can happen. Then you would say that the point P is a essential singularity. The point P is called a essential singularity. So, the next thing says that if no such K exists, then P is called a essential singularity. Now, all this may sound very complicated, but if you look at a couple of examples, you will immediately see that it is pretty simple. Take 1 over z minus 1. Take 1 over z minus 1, correct. So, f of z is 1 over z minus 1. Does limit of f of z as z tends to 1 exist? No. So, 1 is not a removable singularity. After multiplying by z minus 1, so can I say that z minus 1 times f of z, does it have a limit as z tends to 1? Yes. And what is the limit? It is 1. It is not equal to 0, correct. So, the least natural number k such that z minus p to the power k f z has a limit as z tends to p and a non-zero limit, correct. And that number k here is 1. If you take k equal to 2, the limit exists, but it is 0, and 2 is not the least such number. If you take k to be 0, the limit does not exist. If you take k to be 0, the limit does not exist. If you take k equal to 1, the limit exists and is not 0. For any higher value of k, the limit is 0. The least natural number k such that limit as z tends to p, z minus p to the power k f z exists and is not 0. So, point 1 is a pole of order 1. A pole of order 1 will always be called a simple pole. Take cos z upon z squared. What is the troublesome point? The troublesome point is the origin, right? Is origin a removable singularity? Does limit of cos z upon z squared as z tends to 0 exists? No. So, 0 is not a removable singularity. Multiply by z, z f of z. Let us examine what are you going to get cos z upon z. Does it have a limit as z tends to 0? No. Then take try k equal to 2, z squared f of z. What about limit as z tends to 0? Cos 0, it is 1 and it is non-zero. So, what is the order of the pole? 2. So, cos z by z squared is analytic in a punctured disk, and 2 is the least natural number such that z squared f of z limit as z tends to 0 exists and is not 0. So, the origin is a pole of order 2 or a double pole. What about cos z upon z cube? Origin is a pole of order 3 or a triple pole, and so on, right. The next example is a cot z the whole cube. Cot z the whole cube, the origin is a triple pole because z cube cot cube z is nothing but z cube upon tan cube z, and that has limit 1 as z tends to 0. No, nothing smaller than 3 will work, and so the origin is a triple pole. Next example is log of 1 plus z upon z cube. Log of 1 plus z upon z cube exercise show that the origin is a double pole, right. So, when you multiply by z squared, you are going to get log of 1 plus z upon z, and you can actually calculate the limit as z tends to 0. The limit turns out to be 1. So, the origin is a double pole. Is it clear now how to locate and classify the singularities? So, for cot cube z, there are other poles also, no? Pi is also a pole, 2 pi is also a pole, they are all triple poles. So, when you take a differential equation with regular singular points, y double prime plus px y prime plus q of x y equal to 0. When is a point P set a regular singular point? or a point z naught, when is it a regular singular point of the differential equation y double prime plus py prime plus qy equal to 0? When z naught is a simple pole of pz and z naught is a double pole, at most a simple pole of pz and at most a double pole of qz, then you will say that z naught is a regular singular point of the differential equation y double prime plus pz y prime plus qzy equal to 0. Is that right? Exercise: show that the origin is an essential singularity of e to the power 1 over z. No matter what k you take, z to the power k e to the power 1 over z will not have a limit as z tends to 0. Is it clear what is going on? Is the concept clear? You want me to go over any of the example again? Any of the examples? Removable singularity. Take for example, sin z upon z. Okay. The value at the origin I do not prescribe. Limit of f of z as z tends to 0 exists. Sin z upon z is analytic on c minus the origin. Okay. F of z equal to sin 1 over z. What is limit of sin 1 over z as z tends to 0? It does not exist, alright. And so, the origin is not a removable singularity. What about this? What is limit as z tends to 0? Z sin 1 over z? No. It is still not, the origin is still not a removable singularity. Limit does not exist. Take z equal to iy, right? You get? The limit will not exist. So, examine whether origin is a pole or an essential singularity of z sin 1 over z and z cos 1 over z. Or you can take z to the power k cos 1 over z, k equal to 0, 1, 2, etc. Clear? Yes? What is the removable singularity? Limit must exist. Limit must exist. So, z sin 1 over z, limit does not exist as z tends to 0. And so, the origin is a not a removable singularity. Z squared sin 1 over z, z cube sin 1 over z, z to the power 100 sin 1 over z. You would take whatever power, limit as z tends to 0 is not going to exist. Origin is a essential singularity. Origin is a essential singularity. Alright. The study of essential singularity is very difficult, and that goes in the next stage of complex analysis and not in a first course. We are not going to do nothing with an essential singularity. If P is a simple pole of f of z, what does it mean to say that P is a simple pole? It means limit as z tends to P, z minus P f z exists and is not 0. So, now this rho will be called as the residue of f at P. So, if I have a simple pole, then how do I calculate the residue? If P is a simple pole, compute z minus P f of z and calculate limit as z tends to P. That limit is the residue, correct? For a simple pole, the residue is very easy to calculate. And the residue will be denoted by res f of z as z tends to P, or some books use residue of f at P. This is more common. This notation is more common. The residue of f at P. Now, what is the significance of the residue of this pole? Now, you see, P is a simple pole. So, z minus P f z limit exists. So, by Riemann's removable singularities theorem, after multiplying by z minus P, the point P will now become a removable singularity. Earlier, take 1 over z minus 1. 1 is a simple pole. Limit of f of z as z tends to 1 doesn't exist. Multiply by z minus 1, now the limit exists. So, z minus 1 f of z, the limit exists. So, likewise, z minus p f of z, limit as z tends to p exists. So, p is a removable singularity now for the product. Because a removable singularity for the product, p is really not a singularity, but defining the value at p to be the limit, it becomes a analytic function. So, write its power series. What is your A naught? A naught will be the value at p. What have we agreed? We have said that the value at p will be the same as the value will be the limit. We have agreed to assign the value at p the limit. Now, what is the limit? Limit was rho. So, A naught is what? A naught is rho. So, now divide by z minus p and you get f of z equal to rho by z minus p plus a1 plus a2 into z minus p plus etc. It is this part that is very important. This is the part that is not bounded near p. This is a singular part and this whole thing is nice. That is a power series. It is this part that is called the principal part. Okay, this is a dominant part. So, when you have a simple pole, with residue rho, the function f z assumes the following form. It looks like rho by z minus p plus something nice. So, how will cot z look near the origin? What is the nature of cot z? What is the origin is a simple pole, double pole, triple pole. What is the nature? It's a simple pole. What is the residue? 1. So, cot z is going to be 1 over z plus a power series. Cot z is going to be 1 over z plus a power series, right. So, that is how the thing is going to look like near that is the principal part will tell you it's a rational function. Rational function, it's a simple thing like rho by z minus p. The simplest form of rational function is not a polynomial plus a power series is nice. Power series is a nice thing. Then power series plus what? It is 1 over z. The troublesome thing is 1 over. So, the cot z is troublesome at the origin, but it is not bad. It is 1 over z plus something nice. So, the behavior of cot z is like behavior of 1 over z. It is as bad as 1 over z. It is not worse than 1 over z. Cot squared z. How bad is going to be cot squared z? It is going to be like 1 over z squared. Basically, that is the idea. So, now if p is a pole of order k, then z minus p to the power k f z is analytic by definition, because this has a limit as z tends to p. If it has a limit as z tends to p, then by Riemann's theorem, by defining its value at p to be the limit, it becomes analytic. And then once it becomes analytic, I can write the power series expansion. So, you see the power series expansion, I written the first k minus 1 terms and then I written the kth term plus higher order terms, correct. Now, divide by z minus p to the power k. So, what do you get? F z equal to a naught by z minus p to the power k plus a1 by z minus p to the power k minus 1 etc. plus ak minus 1 by z minus p plus ak plus 1 z minus p plus etc. So, from here on you have a power series. Up to this part is the principal part, this is a rational function. And if of all this thing you look at this term, the coefficient of 1 over z minus p, that is the residue. This is not the residue, mind you, please focus on this. Residue is this. Why is it that this is called the residue and not this? Why residue? The reason is will become clear later on in the next couple of slides. The reason is clear. Why is it? Why this particular coefficient? Why not this one? Why not this one? What is so sacred about this? Single power of the single power minus 1, z minus p to the power minus 1. Why minus 1? Why not minus 2? What is so sacred about z 1 over z minus p? Why not call the coefficient of 1 over z minus p the whole squared as a residue. When you integrate, what is the basic thing? Integral over a circle of dz by z to the power m dz. When you integrate z to the power m dz over a circle centered at the origin, what do you get? 0 if m is not equal to minus 1 and 2 pi I when z equal to minus 1. So, the single power in the denominator, that is the only thing that will survive when you integrate over a circle. So, when you integrate 1 over z minus p to the power m dz over a circle centered at the p, centered at the point p, then when will the integral contribute? When for dz upon z minus p, that is only the one, this is the only term that is going to contribute. Suppose I integrate the entire expression around a circle with center at p, then this is the only term that is going to survive. You are going to get 2 pi I times a sub k minus 1. That is why this is called the residue. Well, that is what that remains after you integrate over a circle. Clear? Integrating over an entire circle, full circle, simple closed curve with p inside. So, a k minus 1 is called the residue of f of z at p, residue of f at p, or more frequently it is called residue of f at p. Is it clear? Concept of residue is clear? Okay. Now, let us go back to the previous slide. Now, suppose I take this expression and multiply by z minus p to the power k, then you get this expression, right. So, look at this expression. What is the residue? Where is the residue? It is here, this number, right. Now, how do I capture this number? How do I capture this number? You differentiate both sides with how many times? K minus 1 times, and then put z equal to p, right. So, you have to differentiate. If you have a pole of order p, the rule is if you have a pole of order p, then let me just let me remind you that p is a pole of order k, then you have to multiply by z minus p to the power k, and then you have to take this z minus p to the power k f z, and you have to differentiate it how many times? K minus 1 times, and then you have to put z equal to p. Then the number that you get will be the residue. So, for a double pole, triple pole, etc., calculating the residue involves more work. When it is a simple pole, k equal to 1. So, when you put k equal to 1, you are differentiating 0 times. You are not differentiating it at all. You are simply multiplying by z minus p, and you are taking the limit, right. Putting z equal to p means taking the limit. You can't put it directly because you will get a 0 by 0 form generally. I mean, when I say evaluate this at z equal to p, you have to take the limit as z tends to p, really, right. Clear? This is a very important formula. The exercise, calculate the residue of f at z equal to p in each of the following cases. Please hurry up and write out these exercises quickly. Just write the function and where you have to calculate the residue. F of z equal to 1 over z to the power 4 plus a to the power 4. You calculate the residue at each of the roots of the denominator. The function has a simple pole at each of the roots of the denominator, and you calculate the residue. Take this, do the same thing with the second one. F of z equal to z to the power n minus 1 upon z to the power n plus a to the power n, and p is a root of z to the power n plus a to the power n. So, calculate the residues at each of the roots. Third function is root z upon sine root z. Root z upon sine root z is a analytic at the origin, The root z and the root z will cancel out. So, origin is a removable singularity. Origin is a removable singularity, right? And then the other things, n squared, pi squared, what are they? They are poles. Examine the nature of the poles and calculate the residue. I am giving you the point, n squared, pi squared. When z equal to n squared, pi squared, root z is n pi, no? Plus minus n pi. I am giving you the p. And then take x of a log z upon 1 plus z squared the whole squared at p equal to I. Capital L, principal value of the logarithm. And the last question is cos pi root z minus 1 upon z cube minus z. Cos pi root z minus 1 upon z cube minus z, p equal to 0 plus minus 1. Points are given to you and function is given to you, you have to find the residue. First of all, you have to examine whether there is a simple pole, double pole, triple pole, and then you have to apply the formula. Alright. Next is the residue theorem. Let omega be an open set and function f be analytic on omega minus finitely many points, right? And let us take gamma to be a simple closed curve such that, actually here this doesn't even have to be finite actually, it's can even be infinite, doesn't matter. Let gamma be a simple closed curve not passing through any of the points pj, right, such that the interior of gamma should be contained in capital omega. And the point is f is analytic within and on gamma except possibly at finitely many points. Actually, let's not worry about, let's not try to state the theorem in the utmost generality. Let us just keep it as finite, it doesn't matter. But in all the examples that we will have, we shall only look at these kinds of domains. So there is no need to be unnecessarily fussy about these things. Okay, let us just stick to the original version, not worry about it. So you take a function which is analytic in an omega, remove finitely many points of omega, and take a simple closed curve such that the interior of gamma is contained in omega and the gamma is not passing through any of these troublesome points. All right. So f is analytic within and on omega. So the interior of gamma is completely contained in omega, correct? And f is analytic where? F is analytic on omega except possibly at p1, p2, pk, right? And interior of gamma is contained in omega. So can I say that the function f is analytic in the interior of omega? Yes, except at p1, p2, pk, right? And the function, the gamma is not passing through any of the points pk's, pj's, and the gamma is lying inside omega, simple closed curve in omega. You are taking a simple closed curve in the domain omega, right? And so on the points, on the gamma, the function is going to be analytic. On gamma, the function is going to be analytic because the gamma is sitting inside your domain. Gamma is sitting inside your domain omega. Gamma is not passing through p1, p2, pk. So the function is analytic at all these points on the curve. Interior of gamma is contained in omega, and so the function is going to be analytic in the interior of gamma as well, except perhaps at p1, p2, pk. All right. Then integral of fz dz equal to 2 pi I times summation j from 1 to k epsilon j times residue of f at pj. What is that epsilon j? Epsilon j is going to be 1 if the point pj lies inside gamma. It is going to be 0 when the point pj lies outside of gamma. So let where epsilon j equal to 1 if Pj lies inside gamma, epsilon j equal to 0 if Pj does not lie inside gamma. In short, the integral of fz dz over omega over gamma equal to 2 pi I times the sum of the residues at the poles which are lying inside gamma. Integral fz dz over gamma equal to 2 pi I times sum of the residues of the poles lying within gamma. Only the poles lying inside gamma count, the poles which lie outside gamma can be ignored, they do not count, they do not contribute, right. It is exactly the analog of the Gauss's theorem in electrostatics. The total electric flux over a closed surface equals the sum of the charges inside. The poles lying inside gamma are like your charges that are lying inside are the analogues of those electric charges. The residue theorem is exact analog of the divergence theorem of Gauss in electrostatics. The proof is pretty simple. Let us quickly go through the proof without wasting too much time. What do? You are given a certain curve gamma, right? Simple closed curve, and the picture shows you 3 poles, let us say, are inside gamma. Let us just stick to a simple case. Assume that there are 3 of the poles are inside gamma. What am I going to do? Again, I am going to imitate what we did in the electrostatics business. Draw little circles centered at the 3 poles, correct? Draw little circles. Whatever poles are inside gamma, around each one of them draw a little circle and let the circles all be traced counterclockwise. The original curve is also traced counterclockwise. And then what do? You simply apply the Cauchy's theorem in the region lying in between the two things, isn't it? In this shaded region, you will apply the Cauchy's theorem, correct? In this region, correct? So, what will be integral fz? So, what does the Cauchy's theorem tell you? Integral over gamma minus integral over C1 minus integral over C2 etc. will be 0. Why minus, why not plus? Because these circles are going in the counterclockwise direction. In the original formulation, the domain was to the left of the boundary. It is not. The inside curves are traced in the negative direction. That is why the minus sign. So, integral over gamma minus integral over C1 minus integral over C2 minus integral over C3 etc. whatever is inside. So, if Pj is inside gamma, it will be minus integral over Cj fz dz, that will be 0. In other words, integral over gamma fz dz equal to summation j from 1 to m integral over Cj fz dz, where with a epsilon j. Only those which are inside the curve will count, those which are outside the curve do not count. So, epsilon j is 0 if the thing is outside the curve, equal to 1 if the thing is inside the curve, is right? There the epsilon j comes in. So, now let us say, now as before, if Pj is a pole of order Nj, let us suppose, Pj is, let us suppose, a pole of order Nj. That means what? How does the function look near Pj? What is the situation? The story is, we have already seen this, Fj will look like this rational function plus B naught plus a power series. Right? This part is power series. This part is a power series. So, when I integrate fz dz, is going to be integral of this rational function plus integral of the power series. What will be the integral of a power series? Power series is analytic. So, when you integrate it over the little circle Cj, it is going to be 0. So, this is not going to contribute at all. And so, it is going to be integral of this plus integral of this over a circle centered at P. So, which one is going to contribute? Nothing is going to contribute except B1. So, and B1 is going to be what? Residue of f at Pj. So, integral of Cj over z minus Pj to the power m dz is 0 if m is not equal to 1 minus 1. So, this is not going to contribute, the next one is not going to contribute, this is the only one that is going to contribute. This is the only term that is going to contribute, and the value is what? The value is 2 pi I times B1. It is nothing but 2 pi I times the residue of f at Pj. So, the answer is integral of fz dz over Cj is 2 pi I times the residue of f at Pj. So, integral of fz dz over gamma, which is sum from j from 1 to m, epsilon j integral Cj fz dz, which is going to be 2 pi I times j from 1 to m, residue of fj pj at epsilon j. Remember, I took P1, P2, Pk, and somewhere in the previous slide I said that P1, P2, Pm are inside, Pm plus 1, Pm plus 2, Pk are outside. That is why the epsilon j did not appear. But then, since I did not pay it when I am talking, I did not spell it out. So, I put the epsilon j, no harm. There is no harm in putting the epsilon j. It will simply be 1 for each of these things. And so, I am just putting the extra 1 there in a multiplicative factor, right. So, is it clear? So, in short, integral of fz dz over gamma equal to 2 pi I times sum of the residues of the poles lying inside gamma. This is a simple way of remembering it, correct. This is the residue theorem. This is the exact analog of Gauss's theorem in electrostatics, namely the total electric flux over a closed surface equals the sum of the charges lying inside. So, let us look at a simple example. Calculate integral 0 to infinity dx upon 1 plus x to the power 4. Please do not write this, there will be lots of problems for you, you can do those things. So, you start with f of z equal to 1 over 1 plus z to the power 4. Where are the poles? E to the power I pi by 4. Because I am taking the contour to be, I am going to take my gamma to be this curve, L1 union gamma r union L2. The picture shows you the gamma, and the picture also shows you the pole theta, which is lying inside. What is this theta? E to the power I pi by 4. What is the residue theorem going to give you? Integral over little gamma fz dz equal to 2 pi I times residue of f at the pole. There is only one pole which is inside. The other 3 poles are outside gamma. They do not give you any contribution. So, now you can calculate the residue at the poles, and it turns out that it is minus 1/4 time e to the power I pi by 4. You can calculate it and check. So, the whole thing simplifies to minus I pi by 2 into 1 over root 2 plus I over root 2, right. This much is very clear. Now, we have to calculate the left hand side by actual parametrizing. So, okay, let us do it. So, what is the curve consists of? L1, L2 and gamma r. So, you are going to get fz dz over L1 plus fz dz over gamma r plus fz dz over L2, and the right hand side has been written down, pi by 2 root 2 minus I pi by 2 root 2. That is what we got, no? Right hand side, right. Pi by 2 root 2 minus I pi by 2 root 2, right. So, we just write that down over here. What is L1? How do you parameterize this L1 over here? L1 is simply z equal to x, and x runs from 0 to r. So, f of z is what? Recall what is f of z? F of z is 1 over 1 plus z to the power 4. So, it will be 1 over 1 plus x to the power 4, dz is simply dx, and it runs from 0 to r, correct. So, L1 is easy. What about L2? How do you parameterize L2? First of all, we will have to write the integral over L2 as minus, because it is going from top to bottom. So, you parameterize minus L2 going from bottom to top. What is z? Z is Iy. So, put the minus sign, z is Iy or It. is I dt 1 plus t to the power 4 and t runs from 0 to r. So, if I combine this one and this one, what am I going to get? I am going to get simply integral from 0 to r dx upon 1 plus x to the power 4 into 1 minus I. So, 1 minus I integral 0 to r dx upon 1 plus x to the power 4 is plus integral f z dz gamma r equal to pi by 2 root 2 into 1 minus I, correct. So, let us allow r to go to infinity. Let us allow r to go to infinity. You get 1 minus I 0 to infinity dx upon 1 plus x to the power 4 plus limit of f of z dz over gamma r as r tends to infinity equal to pi by 2 root 2 into 1 minus I. Now, this one will go to 0. Why will it go to 0? Check. How do you integrate over gamma r? Parameterize. How do you parameterize gamma r? What is gamma r? R e to the power I theta. Theta runs from 0 to pi by 2. So, so 0 to pi by 2 r I e to the power I t dt. When I take the absolute values, I will go away, e to the power I t will go away, correct. E to the power I t is going to be here, but then when I take the absolute value inside, that will go away, right. Bottom, what do you have? Mod of 1 plus r to the power 4 e to the power 4 I t, mod of 1 plus z, mod of 1 plus z will be greater than or equal to mod z minus 1. So, that is this mod of this is going to be greater than or equal to r to the power 4 minus 1, but being in the denominator it is less than or equal to r to the power 4 minus 1, and so this goes where? This goes to 0 as r tends to infinity. So, this term is gone, the 1 minus I cancels out. What do you get? Integral 0 to infinity dx upon 1 plus x to the power 4 equal to pi by 2 root 2. Exercise, calculate integral 0 to infinity, calculate integral 0 to infinity dx upon 1 plus x to the power 2m. Use this kind of a contour, no? Similar, instead of m equal to 2, I am taking general m. The sector will have angle pi by m. You will have to integrate over such a circle. This will be your L1, this will be your L2, and this will be your gamma r. And your f of z is going to be what? 1 plus 1 over 1 plus z to the power 2m, correct. Next, calculate integral minus infinity to infinity cos bx upon 1 plus x squared. I take b to be positive, real positive. Compute integral minus infinity to infinity cos bx upon 1 plus x squared dx. Take f of z to be equal to e to the power pi I bx upon 1 plus z squared. And take the contour gamma to be the semicircle, correct. This is your L1 and this is your capital gamma. Integral along the base will give you the integral that you want. Integral along the semicircle will go to 0, and then there is a pole inside, right. Where are the poles of the denominator? F of z equal to e to the power I b z, e to the power I b z upon 1 plus z squared. Where are the poles? Plus minus I. Which one is inside the contour? I is inside the contour, minus I is outside the contour, that is not going to contribute. You have to calculate the residue of f of z at I. So, integral of this is going to be 2 pi I times the residue on the base integral, the base line segment minus r to r will give you in the limit the integral that you want, and the semicircle contribution will go to 0 as r tends to infinity, as in the previous example. Now, question, why do you take f of z equal to e to the power I b z? Why not take f of z equal to cos b z upon 1 plus z squared? Why take this funny function? Why not take cos b z upon 1 plus z squared? The problem is, if you take cos bz upon 1 plus z square, again I is a pole, you can calculate the residue at I, that is not a problem. The base will again give you cos bx dx upon 1 plus x squared, and the base will give you the integral that you want. What do you have to show? You have to show that the contribution from the semicircle goes to 0. That will not happen if you take cos bz upon 1 plus z squared. Because in the upper half plane, what will be cos bz? Cos bz will be cos of bx plus iby, which will be cos bx cos by, and when y is going to be large, because these parts, a large part of the semicircle will be going off up and up. This arch is going higher and higher, and you are going to be having a cos by term. B is positive, and cos by, how does it behave? It behaves like e to the power by, and y and the y is going to infinity. So that you will not be in a position to prove that the contribution from the semicircle goes to 0. That will be a very difficult, if not impossible task. Handling the contribution from the semicircle will be a pain. Whereas if you take e to the power ibz, it will not give you any trouble. You should calculate it and see for yourself. Once again, this is one part of complex analysis that you have to do it. It's only by trial and error that you will understand how to choose the, here I am giving you the contour. Eventually I will stop giving you the contour and you have to find the contour yourself. Eventually I will stop telling you how to choose the function, you have to choose the function yourself. Right? Initially I am telling you both the function and the contour. After some time the contour will not be given to you. After some time the function will not be given to you. And it takes a little bit of ingenuity to do these things. Just as in calculus, how do you know which this substitution will work and that substitution will not work? You can only get it by practice. So I urge you to practice. Please do the calculation and verify for yourself that the contribution from the arc, semicircular arc will go to 0 with this choice. Whereas if you take cos bz, please do it with cos bz and see what difficulty you encounter. Right? Next example. Let us calculate integral minus infinity to infinity sin x upon x dx. Try f of z equal to sin z upon z and you will get stuck. You will get miserably stuck. The problem is that sin z grows very fast along the imaginary direction. So you take instead f of z equal to e to the power iz upon z. Where are the poles? It has a simple pole at the origin with residue 1. And integrate fz along a semicircle with diameter along minus r to r. And I want to integrate along a semicircle, the same semicircle that you had in the previous example. But there is only one problem. What is the problem? The contour gamma is passing through the pole, right? And that is not allowed. So how do I do that? I have to go over the pole, just as when you are riding a bicycle and when you see a pit, when you see a huge pit, do you simply ride into the pit? No. You have to go around the pit and then go on further, isn't it? Isn't that so? Alright. So similarly, we will not do that. We will simply go from minus r to minus epsilon. There is a pole here at the origin. There is trouble here at the origin. We will avoid the trouble by going around the pole. This is called an indentation, a semicircular indentation. Right? And then go on further from epsilon to r and return back via gamma. Correct? Now, f is analytic within and on the contour. If f is analytic within and on the contour, then integral over L1 plus integral over L2 plus integral over gamma plus integral over this other gamma is 0. The function is analytic within and on the contour, right? Is that correct? Now, let us do the parametrization. Let us parameterize it. What is integral over L1 fz dz? What is L1? L1 is minus r to minus epsilon, z equal to x, correct? Z equal to x, dz equal to dx, correct? So, you are going to get simply e to the power ix upon x dx minus r to minus epsilon. What is integral along L2? L2 is what? L2 again is along the real axis, so z equal to x, and then you are going to get fz dz equal to integral from epsilon to r e to the power ix upon x dx. Combine these two things. So, it is simply the sum of these two integrals is minus r to r minus this minus epsilon to epsilon, that small piece has been cut out and thrown away, right? You cut out the small tukda minus epsilon to epsilon and you throw it away, and then you are integrating cos x upon x plus I times sin x upon x. Now, what is this cos x upon x? Cos x upon x is a odd function, so this will drop out and you will simply be left with I sin x upon x. That is one way of looking at it. Or you are really interested only in the imaginary part, the real part does not contribute. So, take the imaginary part of the whole thing. Here is your big equation. From this equation, simply take the imaginary part of the whole equation. So, you will get imaginary part, which is which is integral from minus r to r minus epsilon to epsilon sin x upon x dx plus imaginary part of integral fz dz upon gamma epsilon plus imaginary part of integral fz dz upon gamma r equal to 0, correct. Now, we will have to show that limit of this as r tends to infinity is 0, and we have to calculate the limit of this as epsilon goes to 0, all right. Is this clear? Just write down this double star equation please, so that I do not have to go back to the previous slide each and every time. So, is this part clear? Why we are taking the imaginary part? Because here only the imaginary part will contribute, the real part is not interesting, I do not want that integral. So, in the take that equation star and take the real part, and we are imaginary part, excuse me, and we are left with the integral that you want plus imaginary part of integral fz dz upon gamma epsilon plus imaginary part of fz dz gamma capital R equal to 0. Now, what is the story? The function has a simple pole. The function has a simple pole at residue gamma with residue rho. Let us suppose rho is 1 in this case. So, what is f of z? F of z is rho upon z minus p plus something that is an analytic function. Call it gz. So, integral f of z dz over gamma epsilon is rho times integral dz upon z minus p plus integral gz dz upon gamma epsilon, and gz is analytic. This is easy to calculate, right, directly. Gamma epsilon is a semicircle. So, it is how are you going to calculate it? Z equal to epsilon e to the power it. So, dz will be epsilon I e to the power it dt. Below z minus p will be epsilon e to the power it. That epsilon e to the power t cancels out. You are left with an I, and then you are left, and what are you going to get? The angle through which the thing in this present. So, what are you going to get? Rho I. What are you going to get? Rho I into the signed angle subtended by the arc at the center. Here it is a semicircle, but it could be in other examples. It may not be a semicircle, it may be a quadrant of a circle, or it may be 1/6 of a circle, depending upon the situation. When you are integrating over an arc, you are going to get rho I into signed angle subtended by gamma epsilon at the center, correct, and then plus your gz dz. Now, couple of exercises for you. Check that by parametrizing, check that, I mean I already done it for you basically, I did not write it down, do the writing part. Check that dz upon z minus p integral gamma epsilon is I rho times signed angle subtended by gamma epsilon at center. What do I mean by signed angle? If the arc is traced counterclockwise, it is going to be positive. If the arc is traced clockwise, it is going to be negative. That is a signed angle. In our example, what is the curve? It is the semicircle. How is the semicircle being traced? Clockwise. So, what is the angle? Minus pi. It is minus pi. The second part is show that gz dz integral goes to 0 as epsilon goes to 0. Parameterize. Parameterize. What is z? Z is p plus epsilon e to the power I t. What is dz? dz is I epsilon e to the power I t dt. So, when you put all these things together, what is going to come? Integral gz dz. G is continuous and so it is bounded in a neighborhood. Some call the bound M. What is left over? Dz. What is dz? Epsilon I e to the power I t. When epsilon goes to 0, it will go to 0.